In this example, we're going to create a least squares regression line for a data set that involves male drivers and male crashes and female drivers and female fatal crashes. So let's look at StatCrunch to see how to create that least squares regression line for both males and females. Here is the data set that we want to look at. You'll notice that I have two columns representing information about male driving and fatal crashes, two columns for female drivers and female fatal crashes. And then what we're looking at over here is it's kind of categorized or grouped by age bands. What I want to do is I just want to come up with the equation, the least squares regression line for both the males and the females separately. So in order to do that, it's a similar process that we did before when we created a scatter plot. I go to Stat, Regression, Simple Linear. We're saying that the male drivers are going to be the explanatory variable. The response would be then male fatal crashes. So I have male drivers for X, male fatal crashes for Y. We don't need to do anything else. We'll just click compute and we'll look here. You'll notice that here in the center is all the information we should have recognized from previously, but in this one line here is going to be the equation that we're looking for. We have male fatal crashes is equal to 998.45 plus 0.343 times our male drivers. Now, this piece and component that I keep highlighting here is what I want you to be familiar with, even though we kind of get for free down here with our StatCrunch output windows. It identified for us already the y-intercept as well as the slope. Be sure that you're familiar enough with where slope and intercept fall in our equations to identify them on their own and not falling for or relying on this center component here. So we have our equation we want to identify, and I want to do the same thing for the female crashes. So I can either exit this and regenerate it, or I can change the X variable to now be the female drivers with the female fatal crashes, and I can hit compute, and you'll see that I have the same type of an equation listed for us right here. So here are those two output screens that I created in StatCrunch for us on the screen that you see. In the left, I have the equation representing the male fatal crashes, and on the right, I have the least squares regression representing female fatal crashes. Now we want to be able to interpret the slope. So we want to make sure, first of all, that we have the equation written down. So I have put the equations up here on the screen for us. Remember that this equation that we're looking at on the left, this y hat sub m, is the prediction equation representing what we think is going to happen for the male drivers. We are predicting male fatal crashes here with this equation, and we are predicting female fatal crashes here on the right. So we want to interpret the slope. As we've seen previously, in order to interpret the slope, it's easiest and helps us organize our thoughts if we write them in that ratio of y over x, which is how we define slope. So our y values represent male fatal crashes. Our x value or explanatory values represent male drivers. So I have put into this ratio the value for slope, which we can see came from my original equation of 0.343. So 0.343 for the male fatal crashes over 1. I'm always going to write the slope over 1 male drivers. And now I need to be able to come up with a sentence that describes or interprets this slope for us. This is an example of what we might see, specifically talking about the males. If the number of licensed drivers increases by 1, then the number of fatal crashes increases by 0.3428 on average. Now, I didn't highlight or point out the fact that the spreadsheet that we used in StatCrunch, all of those drivers that we were looking at for both the males and the females, they were per 1,000. So a lot of times in statistics or when you have a data set, they'll just drop those 3 zeros representing the number 1,000 to make your numbers a little easier to handle. So this is how I would interpret then the slope for our male equation. A similar process is going to happen for females. Recognize from our equation, either here highlighted in yellow or the one we rewrote underneath, that 0.105, so 0.105 is going to be in the numerator now over 1 in the denominator. Interpretation might look something like this for the female drivers. If the number of licensed drivers increases by 1,000, then the number of fatal crashes increases by 0.1045 on average. In looking at both of those sentence structures, we once again have identified in words what the explanatory and the response variables are, and we have told by how much specifically each of those variables are increasing or decreasing if necessary. So the next part of this question just simply says, well, how might insurance companies use that information? In looking at this, it's easy to identify that you're going to have more fatal crashes for men than you would women. So, since females tend to be involved in fewer fatal crashes, an insurance company may use this information to argue for higher rates by gender, so for males. Now let's look at interpreting the y-intercept for each of these genders. So what you see on the screen here, you have your predicted fatal crashes for the males, the equation for that least squares regression line from the previous screen, as well as the predicted fatal crashes for the females from the previous screen. Remember that in order to interpret the y-intercept, we are saying that the x value, so number of drivers in this case, would have to be 0 in order for me to get, in the male side, 998 fatal crashes. So that doesn't exactly make sense to interpret it in this context, right? 0 drivers for still 998 crashes. So we would just simply say it doesn't make sense to interpret this in this context. Moving on, we want to look at these two questions here. We want to determine, was the number of fatal accidents for the 16 to 20-year-old males above or below average? In order to do that, I need to understand what it is we're looking at. So I'm going to pull up our spreadsheet table we were looking at from StatCrunch. And remember, here is the column represent all the male drivers. Here's the column representing all of the fatal crashes. And then if we look at the rows, it's subdivided by ages. This is the actual data. So this is actually the number of drivers, and these are actually the number of fatal crashes. We want to, in this particular question, identify this information for the 16 to 20-year-old band. So we're going to look at this information here. The 6424 represents the number of male drivers, and the 5180 represents the actual male fatalities. In order to compare whether these male fatalities that actually happened is above or below what we expect to have happen, we need to refer back to our predictor equation here from above. So we're going to take that equation, the equation that's predicting the average fatalities for males, but we're going to substitute in the 6424 as the number of drivers representing the 16 to 20-year-old bands, or the 16 to 20-year-olds. It's during that number. So this is X, right? X represents our male drivers. So the 16 to 20-year-olds had 6,424 drivers. When we multiply that out add our y-intercept, we end up with 3,200 predicted fatalities. Now, how does that compare to what really happened? We're going to take the real value minus our predicted value. The real number of fatalities for the 16 to 20-year-olds was 5,180. We predicted, based on 6,400 drivers, that there would be approximately 3,200 fatalities. So our number of actual data, the observed data, ends up giving us a positive value, so we would say that it is above average. Let's do that again, only this time we're going to look specifically at the 21 to 24-year-old males. So this time I'm going to look at the next row. There were 6,941 male drivers and 5,016 fatalities. We first want to predict the number of fatalities given the number of male drivers that we had here. So to the original equation that we created, right, the original least squares regression line for this relationship, we're going to substitute this time the 6,941 drivers for this age band. We calculate this out using the formula, and we see that we predict there's going to be somewhere around 3,300 fatalities for the men when we had 6,941 male drivers. We take the real value of fatalities minus the predicted value. So real fatalities was 5,016. Predicted fatalities is 3,378. We can see that that's going to give me a positive value. So once again, we would say that the actual fatalities is above what we would expect for an average. One more example. Was the number of fatalities for males greater than 70? Was the number of fatality accidents for males greater than 74 years old above or below average? So we're doing the exact same thing again. I've put our equation for the males up here at the top. Remember, we need to predict how many fatalities are there going to be for 4,800 male drivers. So you can see from the equation here, we have 4,800 male drivers for the over 74 age band. We're going to predict there's going to be approximately 2,600 male fatalities. Let's compare that to what's really happening. So real minus predicted. In actuality, there was 2,022 fatalities. We predicted, however, there were 2,600 fatalities. When I subtract that, I have a negative value. So we would say then that the 2,022 fatalities for this age band is actually below the expected average. So how do we think insurance companies might use this information? Well, if you noticed, the age bands for fatalities for the males for the 16 to 20 as well as the 21 to 24-year-olds was above average. So they had a higher than normal fatality crash rate, whereas the over 74-year-old males had a below average crash rate. So insurance companies will generally use this type of information to be able to argue for those higher rates for younger drivers, and then they end up lowering the rates for older drivers. And if you were to go back through and do the same process for the females in the exact same age bands that we've already done, you would see a similar relationship holds for them.